Okay, lads, here we go. This is taking our ChemCubby, which we did, I think it was last week, and we're taking it to an entirely new level. So let me get it started here. What we're going to do is we're going to burn some octane, which is the stuff in your car, and we're going to burn it in oxygen. We're going to make carbon dioxide and water, and we're going to burn a certain amount, and we're going to find out how much of two things. First, how much oxygen in grams are we going to need? And also how much carbon dioxide and water are produced. It might seem a little tricky at first, but if you follow along, it shouldn't be too bad. So let me write down what we know first. So again, here's what we have. We're going to burn 23.45 grams of octane, C8H18 in oxygen, to produce carbon dioxide and water. Now, first of all, what we need is we need an equation, and then we need a balanced equation. So let me show you the equation, and then we will balance it. So here's the equation. We've got our reactants being octane and oxygen, products being carbon dioxide and water. Now we need to balance this equation, and for the sake of brevity, I'm not going to go through the entire balancing process, but instead I'm just going to add in the coefficients that go with this. So here's our balanced equation. We need 2 octanes, 25 oxygens, 16 carbon dioxides, and 18 waters. And that is the balanced equation. That's the amount necessary to make this reaction work. Now again, what we have is 23.45 grams of octane, and if you remember, I told you we want to know how much carbon dioxide we're going to produce, and we also want to know how much water is produced and how many grams of oxygen that we're going to need. So here's our ChemCubby. If you remember, the ChemCubby is going to look something like this. So this structure should look somewhat familiar to you. And we did it with the tricycles. You can look back in your notes if you want. Pause. And by the way, guys, anytime during the filming of this, if you have a question or you need to look at something, you may pause it and go back, whatever you need to do, right? That's the beauty of what I'm about to do here. So, we're going to set it up, but slightly differently this time. In the first box, we're going to write the word amount. Middle box, we're going to do what's called the conversion factor. And in the third box, we're going to do moles. So this is very different from when we were making tricycles. We're now going to try using amount, conversion factor, and moles. And if you remember, we had a star in one of the boxes. And the star was what we started with, right? Remember star, start? So we started with 23.45 grams of octane. And we're going to put a star there. And notice that below each box corresponds to our balanced equation. And everything that's in there will correspond accordingly. So let me get rid of those. Now where are we going to proceed from here? If you notice, I change colors here, we have something called a conversion factor and we have moles. So we're given an amount in grams, and we need ultimately to get to moles. And how are we going to do that? What's the conversion factor we're going to use? We're going to use the conversion factor of the molar mass. What is the molar mass of octane? So, and that would be C8H18, and I'm going to look that up, and I'm going to make the calculation, and I get 114.26 grams per mole, and that's for 8 carbons and 18 hydrogens. Now, very simply, I'm going from grams to moles, so GMD, grams to moles, I'm going to divide. What am I going to divide by? I'm going to divide the 23.45 by 114.26, and I'm going to get 0.2052 moles of octane. Now, if you notice, I didn't label where it says grams. I didn't label any of this with what it is, because we are in the octane column, so all of these things deal with octane. So I'm not going to write down the specifics on it. I need the units, but I'm not going to write down units of what because that's in the right above in the column heading. Now, this tells us here, we want to know how many grams of oxygen are needed to make this. So watch what happens here. If you remember, we have a 2 to 25 ratio of octane to water, or to oxygen. And what that means is for every 2 moles of octane that I'm going to burn, I need 25 moles of oxygen. So when I go this way, from moles here to moles here, I start with where I'm going. So it's a 25 to where I've been over 2 ratio. 25 over 2 ratio, which means I need 25 oxygens for 2 octanes. And so when I use that ratio and the number, I have 2.565 moles of oxygen are needed to burn 0.2052 moles of octane. And again, how did I get that? I took my 0.2052 moles of octane, I multiplied by 25 moles of oxygen over 2 moles of octane. So it's 25, so I get 2.565 when I make that calculation. I want to know grams, which is up here in this box. So what's my conversion factor? What's my conversion factor? How am I going to get from moles of oxygen to grams of oxygen? Oh, yeah. Oxygen is 32.00 grams per mole. And when I take moles to grams, I multiply. So I'm going to multiply my 2.565 moles of oxygen by 32 grams. And I'm going to get 82.08 grams of oxygen. So I need, for every 23.45 grams of octane, I'm going to require 82.08 grams of oxygen. So you can see, since octane is the stuff we burn in our cars, it requires 12.5 times as much oxygen. So we go through a lot of oxygen in our daily lives when we drive our cars, 12.5 times as much octane. So it is an oxygen gulper, as it were. Okay? Now next, we were asked how much carbon dioxide is there? I think you already have an idea as to where we're going to go with this. So I'm going to go, boom, from here to here, from octane to carbon dioxide, and it's a 16 to 2 ratio. Now, yes, for you guys that are answering, and I'm sure some of you that are questioning, some of you guys, we could go this way. We could go from oxygen to carbon dioxide, in which case it would be 16 over 25, right? And either way, we're going to get the same answer. Trust me. So 16 over 2 times 0.2052 is 1.642 moles of carbon dioxide. Very good. So again, just like here, we take our moles, multiply by our ratio of where we're going from where we came, and so we take 0.2052 multiplied by 16 divided by 2. Good. What's our conversion factor? Now we want grams. Again, we're going up here. What's our conversion factor for carbon dioxide? Most of you probably already remember this because we've used it a lot. Very good. It's 44.01 grams per mole. And if we multiply 44.01 times our 1.642 moles, we get 72.76 grams of carbon dioxide. Okay? There you go. How easy this is. So the conversion factor as we go all the way across in this case is always going to be the molar mass of whatever it is that we have up here. And it's only 1 mole, remember, right? We're not using the 18 here. We're not using the 16. We're not using the 25. We're not using the 2. We're only using that down here is our ratio. Now finally, we want to know how many grams of water we produce. So just to save space, let's go from carbon dioxide to water. It's an 18 over 16. I don't know if you guys can see that. Let me try a different color. That seems to be a little easier to see. 18 over 16 ratio, right? So when I take 1.642 moles and multiply it by my ratio, I got 1.847 moles of water. And you can probably do this in your sleep now. How many grams are in 1 mole of water? Good. 18.02 grams of water are in 1 mole of water. And when we multiply those two together, we get 33.28 grams of water being produced. Very good. So, gentlemen, that is how one uses the ChemCubby. Now, what I'm going to do next is I'm going to set up a cubby with an equation. And just see, write this in your notebook, see if you can figure out how to do it. So just one moment, please. So here's our problem. We're going to burn 56.78 grams of octane in oxygen to produce carbon dioxide and water. How many grams of water and carbon dioxide are made? Again, we have our balanced equation. Try to keep this easy on you guys by keeping it the same. We have our amount, we have our conversion factor, and we have our moles. Now, where do we, I'm going to ask you to pause and work on this on your own as I ask the questions. Okay? So first of all, where do we start? Good. We have the 56.78 grams of octane. What's our conversion factor? Now, how many moles of methane is that? Or excuse me, of octane is that? We're asked how many grams of carbon dioxide do we need? So let's make that calculation now. Again, pause as you go along. Next, figure out the conversion factor and then how many grams of carbon dioxide are needed. And so there we go. Further, we are asked how many grams of water are produced. Good. And then follow up with conversion factor and then the number of grams of water. And we have 80.59 grams of water. So gentlemen, that is how you solve what we call a stoichiometry problem. Stoichiometry problem is where we start with certain amounts and we work our way through and figure out how much of the other amounts we may need. So thank you very much. Replay as necessary, and I will see you in the morning. Thank you, gentlemen.